Hi, everyone. Our work is titled The Myth of the Pyramid. I come from the south of Mexico, from the Mayan area. So we have a lot of pyramids there. And we always ask why they did that buildings in that form. Hopefully we can figure out why. And in this work, we have found that design in a lot of convolutional networks. So we ask as well why this design is present in all those architectures. So it is generally believed that a progressive increase in the number of kernels compensates for a possible loss of the representation caused by the spatial resolution reduction, as well as improves performance by keeping a constant number of operations in each layer. This pattern can be observed in a diverse set of models like BGG, ResNet, and MobileNet, and even models obtained for neural architecture search, such as NASNet, follow this principle. So it has been taken for granted that this design is optimal for all models and datasets, at least in the computer vision domain. To challenge that myth that the pyramidal distribution is of universal applicability, we evaluate a small set of predefined distribution that we call templates on several node datasets. These patterns are defined with very simple linear and piecewise linear functions, which enables designers to easily implement them on most of the existing CNN models. The patterns are not arbitrarily selected. They are inspired by designs found in previous works and by running automatic model discovery methods. Following the findings in the PyramidNet paper, we reduce a step change in all the patterns in our experiments. So we have found that this smoothness improves accuracy in almost all of our models. So our first approach to change the filters in an architecture was to keep the original filters in the resulting model, but redistribute them differently across the layers. Nevertheless, final models end up with different resource demands, and therefore making fair comparisons was really problematic. So we believe that using one metric is insufficient for impartial comparison. As examples, for process-intensive datasets, our implementations of BGG and ResNet count an approximate number of parameters, 20 million versus 23 million. But the ResNet flops are more than 3 times the BGG flops. To facilitate evaluations, we matched one metric well compared to the other. In particular, all models obtained from templates match the flops of the original model. And then we compare other metrics, such as accuracy parameters, memory footprint, or inference time. In this example, we show the final number of filters in each of layer of BGE model modified with templates. We see the increasing A template differs from the original in the smoothness of the change. The uniform distribution set all filters to 153. In all cases, the minimum number of filters in a layer for the whole model matches the minimum number of the original base designs, 64 in this case. This prevents a model suffer from representational power loss cost for the bottleneck effect. The experimental results show improvements in accuracy and resource consumption for BGE and ResNet architectures in all of the 6 datasets evaluated. In some cases, reaching higher accuracy with up to 65% less parameters. These results show the positive effect of different distributions despite the template patterns were selected following simplicity and diversity, but not focus on efficiency. We know that both MobileNet and MNASNet perform best in tiny ImageNet datasets. We believe this is because tiny ImageNet is strongly related to ImageNet, and designs have been optimized to the latter. However, template A is still competitive with reductions of 1.5 points in accuracy, but savings up to 49% in parameters. In the audio classification domain, by using templates on ResNet, we got improvements in accuracy between 1 and 2% over the base models, we highlight that template C in GTs and obtaining a similar accuracy with only 14% of the original parameters. We compared the best model in the NASBench dataset. It contains more than 400,000 automatically discovered CNN networks evaluated on CVPR10. The search space of NASBench is restricted to this pyramidal distribution of filters. Template C obtains a higher accuracy than the best performing model with 1/3 of the parameters. Yeah. Of course, we are not aiming for templates to outperform any neural architecture search method. We state that combining templates with search methods can deliver further improvements to final CNN models at a very low cost. In all the experiments performed in this work, the templates use similar flows than the original architecture. So in summary, this work challenged the pyramidal filter distribution present in many neural networks by using a set of varied templates that modify the original filter distribution. For almost all case tested, template models delivers best performance and reduces resources with advantages that go beyond the domain of image classification. The experiments indicate that for each model tested, there is no particular distribution of filters that guarantees the best accuracy on all tasks. This means results of automatically searching for the number of filters in a small dataset, such as CVPR, should be carefully extrapolated to other datasets. In the opposite direction, models with distributions that work well on extensive datasets should be changed with templates, for example, to perform efficiently on different domains. That's it. Thank you.
Yeah, go ahead. I was wondering why you didn't consider pruning network at the baseline?
Well, the main difference is that we just propose to open the search space for neural designs. Pruning networks have let's say a cost of finding what is the best nodes to prune, and here we just adjust the filters, and that's it. You train the model, so there are no hidden costs.
Yeah. Next question. I see that you mainly focus your work on convolutional networks, right? How do you transfer your learnings into the vision transformers? If there is any way to apply it?
Yeah, well, the transformers, starting they don't use the pyramidal design. They use uniform design. So I haven't worked on them. I couldn't say that. Yeah, but if they have a number of modules, not filters really, but modules, you could try just to change the number of models in each step.
So in theory, we should be able to find similar kind of templates, right? If there is a transformer architecture.
Yeah, actually, what we wanted is just to open the search for new designs, not to propose a technique for finding the best templates.